Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we inject weird and wonderful science directly into your genes. I'm Ian Woolf. On this edition, I speak with Noushin Nasiri and Naomi Belic about science communication, and use a time machine to interview the 2018 Australian of the Year before she was famous. But first up, here's the news about bacteria communicating electronically. Electrogenetic devices. Researchers at the University of Maryland have engineered E. coli bacteria to exchange signals electronically instead of biochemically. This allows the researchers to instruct the bacteria to swim and to express genes on demand. The researchers imagine in the future that you could swallow a microelectronic capsule that could record the presence of a pathogen in your gastrointestinal tract and also contain living bacterial factories that could make an antimicrobial drug or other therapy, all in a programmable autonomous system. Or even further into the future, electromagnetic switching might let us interface more directly with our machines. The researchers are using a redox molecule called piocyanin. Piocyanin can transport electrons either by undergoing a reduction reaction and gaining an electron, or an oxidation reaction and losing an electron. They used a second redox molecule, ferricyanide, to amplify and stabilize the signal. The same researchers previously used redox molecules to sense an environment and report back electrochemically. They sent out redox molecules from electrodes, let those molecules interact with the microenvironment near the electrode, and then drew them back so they could inform the device on what they'd seen. It's a little like sonar, where redox molecules are used instead of sound waves. They use this technique to identify pathogens, monitor the stress and blood levels of individuals with schizophrenia, and even determine the differences in melanin from people with red hair. For these experiments with engineered bacteria, the researchers used a microelectronics device that used an electrode to apply a positive 0.5 volt charge for an on signal and a negative 0.3 volt charge for an off signal. The researchers tested the bacterial electrogenetic device by instructing it to express a gene for a fluorescent protein, effectively making the bacteria turn a light on or off on command. Next, they engineered the bacteria to express a gene for the CHEZ key Z protein that causes the bacteria to swim forward. The bacteria went faster with more of the protein. They were able to slow the bacteria by decreasing the production of the key Z protein when they sent a negative signal. They measured the changes in movement of the bacteria with video recordings that were analysed frame by frame. Finally, they engineered the bacteria to respond to an electronic signal by communicating with other bacteria, a process known as quorum sensing. When the engineered bacteria received the electronic signal, they sent biochemical messages to bacterial cells nearby that in the experiment caused those nearby bacteria to light up with fluorescence. Previously, researchers have engineered first bacteria and then later nerve cells to respond to light with optogenetics. Electrogenetics requires much less genetic rewiring and is based on cellular machinery already present in the bacteria. Being able to send and receive electronic signals could let bacteria and other cells be used in sensors to detect disease and also be used as a treatment to release proteins on demand, or even tell other bacteria how to behave. The paper was published in the journal Nature Communications and was titled Electronic Control of Gene Expression and Cell Behavior in Escherichia coli through Redox Signaling. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Noushin Nasiri is a postdoctoral research fellow from the University of Technology, Sydney, who's developing nanotech sensors for your breath. Naomi Belic is a stem cell researcher also from the University of Technology, Sydney, who uses stem cells to build a disease-in-a-dish model of multiple sclerosis. Both Naomi and Noushin have participated in the FameLab training and competition to present their research on stage. I began by asking Naomi, what did you learn from FameLab?
What did I learn from FameLab? There is a lot. I think the best thing, obviously, is how to be a good communicator, and it gives you really tangible skills. But it also teaches you the importance of science communication, so why we need to get our science out there in the first place, and that is incredibly important.
And how did they teach you? What was the process?
So they teach you how to walk on the stage, how to have an eye contact with every single audience sitting in front of you, how to look at your own research from different perspective, because you are doing that research. There are lots of things that are kind of normal and like sometimes even boring to you, but that thing might be quite interesting and also quite exciting for general audience. From the other side, there are lots of things that you think is okay. Everybody knows about that, but you are wrong, So they teach you what is the general audience knowledge, what is the public knowledge about your own research, and then what is the expectation from you, how you can deliver it in terms of having the scientific part, but make it simple to be easily understood.
And what sort of length of time were you supposed to be on stage for?
So because this is super accessible science, it's only for 3 minutes that we're up there, which is pretty intense, jamming all your science into 3 minutes. But you quickly realise 3 minutes is an awfully long time. That's like a full song. There is so much that you can let someone know in that type of time frame. So it's about learning those skills about how to be concise, not to use jargon and just jam scientific words down people's throats. Because science is really interesting and you should be able to explain anything you're doing to anyone.
What other experiences have you had other than going for just 3 minutes on a stage? Well, even FameLab was more than 3 minutes on a stage, wasn't it? Did they have you talking to other people as well as your stage performance? Or was it just preparing you for the stage?
Yeah, it's like preparing you for the stage. It's like giving you the confidence, the confidence of... For me, actually, it was looking into my research in a different way, because when you have to explain your research in 3 minutes in a simple way, you start thinking differently about your own research, because now you want to explain everything, but you have to be careful that if you go for too much details, it's going to be boring. It's going to be like, okay. So it's a very good practice in terms of how you present it, what to present, and then always look at your audience, who are your audience, because it depends. If you are presenting in a high school, your presentation should be different than you're presenting to the bunch of professors, or you're presenting to business people. So they teach you that the audience are really important. Your research is important, but not as important as the audience. They are the goal. They have to, if they leave the room and then keep talking about your research, then you are a winner.
So you have to have a model of the audience in your mind while you're speaking.
Yeah, you definitely do.
In order to know what sort of language to use, what sort of words, and how do you do that? Do you have a little, like a little person at the back of your head going, oh, I don't understand that? Or what's your process?
To be honest, the best way for me to really understand if I'm using too much jargon or being too complex is I just go and pick a friend and I make them sit down and listen to my talk. So a fresh set of ears are the best way to decide how you should describe your science. And the interesting thing is, the more I get into science communication, the more that I try and explain my science in a simple and accessible way, I realize that even doing the same, adapting those techniques to when I'm talking to things like professors, it makes my science more accessible to them as well. Like, I don't need to use excessive amounts of complex terminology when I can explain my science really simply.
And from FameLab, you went on to a bit of a longer presentation.
Yes, actually, after FameLab, you actually have a chance to be heard by other people as well. And there are lots of other organizations, people are looking for science communicators. And one of them is TEDx Sydney. And then, after FameLab, I think it was like less than a year, that I've received an email and an invitation to go for TEDx, to present my research in TEDx Sydney. And that was like fantastic. But, it happens to you if you start doing this science communication. So people, they approach you one after another. If you start doing this science communication, if you go to this science communication journey, and one of the best way to start this journey is FameLab. The reason is you have a chance to be trained. For something like TEDx, you have to be trained, or you have to be trained already. They don't have time to train you, So they choose you if you are a science communicator already. But for some competitions like FameLab, they have a group of people, very professional, experienced people, that they teach you. They're not expecting you to be a science communicator at that moment, but they teach you to become a science communicator after FameLab.
And TEDx, for the audience who haven't heard of it, that's an external version of TED, the education and
Exactly. So TEDx is the TED Talk in each city. So it's TEDx Sydney, but we do have TEDx Canberra and TEDx Melbourne in Australia as well. But yeah, because I was in Sydney, I've been invited by TEDx Sydney to present my research.
And how long was that talk for?
It is something between 10 to 15 minutes.
So very different to a
Yes, it is.
presentation.
Exactly, yeah. And this is not a sort of kind of competition. This is sort of talk about your research, present your research, again, in a way that the general audience can understand it, because in the audience, you have a variety of people, different groups of people from high school to the retired professors from the university, and you have to make sure that your presentation is going to be interesting for these all different types of group.
And this is on YouTube?
Yes, this is on YouTube, yeah.
And did you use slides?
Yes, you do have a chance to use slides. So not too many slides because it's going to be boring. There is no rule, but it's better to have some slide that helps you to deliver your message easily and perfectly. Yep.
And do you have an opinion, Naomi, on the use of PowerPoint and slides when you're talking?
Oh my goodness, it is so interesting having a slide or a prop or something there to engage with, but that can also really easily be abused. There's so many times that I sit down in a lecture or in a conference and there's an amazing speaker I'm so excited to see, and they start and there's just walls of text. Things like that, just they break me. So it is a great opportunity to explain yourself and really get people engaged, but you need to be really careful about the way that you use it.
And Naomi, you've also gone on to other things after FameLab with the media.
Yeah, I've definitely caught the science communication bug. I can't help myself. I just keep on doing it. So I got picked up by some exciting projects. So I've worked with Discovery Channel and with ABC. My most recent project being ABC Sciencey, where I even get to actually interview Noushin, so you can hear all about her research and other stuff that's happening in the world of breath science. But I've fallen in love with science communication so much, I actually wanted to adapt that to my current PhD. So I work in the area of multiple sclerosis, and I realized quite quickly that it is really dang hard if you want to know more about multiple sclerosis. So you hop online and there is a lot of information there. But it's almost like there's too much information. It's hard to tell what's real, what's reliable, and find things that are accessible and easy to consume. So what I've pretty much done, it's very early stages, but I've teamed up with MS Translate. So that's a company based down in Melbourne, and we're creating a series of videos explaining the basic science behind multiple sclerosis. And the way that this all ties into my research is that I've also teamed up with some researchers from UTS as well, and we're going to be looking at how this digital media actually improves their learning and how these participants all self-regulate their learning. So it's really exciting. I've fallen in love with science communication, and now I've even had the opportunity to adapt it to the research that I'm doing right now. So I'm definitely on the science communication train.
Wonderful. And your research, what sort of people are you going to get in to do that?
So it's very, very early days now, so we're still discussing exactly how I want to enroll participants, and that's still downstream, so a few months away. But to be honest, it's less about how we... It's less about the participants that we get involved and more about how we extrapolate the data downstream. So really, if anyone wants to do it, they're more than welcome to participate.
So what's up next for you with science communication?
Yeah. When it comes to everything I've done in science communication, I have honestly never planned it. These things just fall into my lap and they pop up so quickly. So I am sure there are things on the horizon, but I have no idea what's there, and that's half the fun. If people want to get more engaged in science communication and see some new science that's coming out, FameLab runs in every single city in Australia. So all the major cities, you will find a competition there for you. I have no idea the dates because they're all different, but it's a great chance to actually see some new young scientists and find people to follow and find new areas of research that you're really interested in. The national finals are live streamed as well, so no matter where you are, you can tune in and have a look at that as well. So that's really exciting. I mean, Noushin, actually, you watched my live stream. I remember on Twitter you posted a photo and I was like, oh my God, Noushin's watching me.
Yeah, and you can participate by voting, because there is an award named People's Choice Award. Even if you are not there in the room, you can just watch the live stream, and then you can choose your favorite talk and then vote for it.
And of course, if you go online, you can pretty much find out where these events are being held, and they're free.
Yes, so it's all through the British Council.
Well, Noushin and Naomi, thank you very much.
Thank you.
Thank you.
That was Noushin Nasiri with her nanotech sensor detecting diabetes on your breath, along with Naomi Belic with her disease in a dish, both conducting their research at the University of Technology, Sydney, and addicted to science communication.
John, what's happening to us?
I think we both know, Mary.
It's just that we seem to be drifting apart.
I'm sorry, Mary. I've tried.
Oh, I don't blame you, John. It's just that...
It's not your fault either, of course.
It's just that we don't have...
Exactly. There's this awful gap in our lives just because we don't have... Oh, but why talk about it?
It's just that... Oh, I keep hoping someone can find a way to...
Don't be a fool, Mary. You know that's impossible.
Oh, I know. It's just that...
Gad, it's ironic. With all our technology and industrial know-how, we still don't have the one thing that could give us a better way of life. They say it can't be done, that it's just an impossible dream.
Professor Michelle Simmonds is a Scientia Professor, Australian Research Council Laureate Fellow, and Director of the University of New South Wales Centre for Quantum Computing and Communication Technology. She won the 2018 Australian of the Year Award, so she's currently too busy to talk with me. I jumped in my time machine and went back to the first International Nanotechnology Conference and Exhibition held in Sydney in 2002, before Michelle Simmonds was famous. And I spoke to her about her work in understanding the mystery of why transistors work and building a silicon-based quantum computer.
So really what we're trying to do is to understand how transistors work. I mean, it's something that you may think we all should understand because transistors form part of the everyday computer. And there are typically about 13 million transistors in a modern Pentium 3 processor. But despite the fact that there are that many of them, if we really go to try and understand how they really work, whether they behave as metals or insulators, we don't understand right at the basic level. So at room temperature we can understand how they work, but the actual quantum properties, if you cool them down, we're lost. We've got no equations to describe their behaviour.
So we've had transistors for 50 years, and we use them every day in everything from, as you said, Pentium 3s to VCRs to transistor radios to everything, and we never really understood how they worked.
Yes, it's basically understanding the fundamental nature of how the electrons move inside the transistor material. So what we tend to find, one of the things that was amazing back in the 1980s, was they found that if they took a piece of metal, such as gold, and they thinned it down to 100 angstroms, which means basically you've entered the quantum regime, you've actually confined the electrons to move in like a sheet of paper in a two-dimensional plane. They found that even metal, when you thin it down that thin, actually stops conducting electricity. And this was something that they just couldn't understand. How could something that you know to be metallic suddenly become insulating when you thin it down?
So all the rules change when you get down to the very tiny quantum level.
Exactly, that's exactly what's happening. And what we tend to find is that not only do the electrons in the device behave like particles in the way that we normally expect, but they also behave like waves. And it's this wave nature that gives rise to all kinds of interference effects in the two-dimensional plane, which can stop the whole system conducting.
So the waves start to interfere with each other and they stop the conduction altogether, so you get a metal that's not a metal anymore, or a semiconductor that doesn't conduct at all.
That's right. It's very difficult to explain, but essentially when the electrons are confined into a two-dimensional plane, they can't escape from it. And what tends to happen is that any impurities in that plane cause it to localize. And because it's a wave, you get these little ring structures in the two-dimensional plane, little circles that form, which means the electrons can't get from one side of the device to the other.
So you're saying that when the electrons, if they're in a three-dimensional device, they'd be able to go up or down, but because they're stuck in a two-dimensional flat sheet, they can only go forwards or backwards or side to side. And when they get stuck in these rings act, I'm thinking almost like a pinball machine where there's obstacles in the way and they can't get past.
That's right, exactly. They actually, we call it localized. They get stuck to a certain part of the crystal and they can't pass through from one side to the other. So it all becomes insulating.
So if you do understand how these work, what's really going on, where can this lead you with electronics in the future?
That's a very good question. Really, you need to understand how things work so that you can predict, if you make new kinds of structures, what's going to happen in them. And one of the things that I'm doing really is basic fundamental science, and it's obviously difficult to predict what's going to be the future. So, but all the different structures that we make, so we can make, for example, one-dimensional wires, and we can make what we call zero-dimensional dots. And understanding how each one of those behaves really means that we have to understand how it behaves in a two-dimensional system first, and then keep confining it and see what happens. So originally, for example, there's an effect called the quantum Hall effect, which won the Nobel Prize in 1980. And that really was something that nobody had understood until that point. And they found that if they looked at the resistance of a two-dimensional plane in a magnetic field, they found that they had these discrete quantized levels that occurred at exact values no matter what the material system was. And before they looked at the quantum systems, they had no idea that was going to turn up. And now there's theories behind that can explain why that exists in a two-dimensional system, and it's actually used in an application now. So it's actually used in order to measure resistances. It's the resistance standard now. They use this quantization of the resistance in a two-dimensional plane as the basis for calibrating all resistors in the world.
So when you say the resistance is quantized, you're saying there's different levels, so these different levels occur at different voltages, or? They
essentially, yes, at certain magnetic fields, depending on the material that you're using, you find that the Hall resistance, the resistance across the two-dimensional plane becomes quantized. It reaches a certain value of about 25 kiloohms, and it's fixed at that value for a period of time in magnetic field.
So it's quantized according to the amount of time. I'm just trying to see where the steps change.
It's basically a step change with magnetic field. So as you increase the field, at different fields you find different quantized levels.
Right. So you can measure the field.
Yes, that's right.
And you mentioned zero-dimensional dots. Would this be related to quantum computing?
Some people are actually trying to make quantum computers with zero-dimensional dots, but one of the things that I also do is I work in the Centre for Quantum Computer Technology, and there we're trying to make a quantum computer in silicon. And really what we're using in this situation is you have to make something that's very small, something called a quantum bit, or a qubit, and that's actually made of phosphorus atoms in silicon. And what we're relying on there is the spin of the phosphorus atom being in the qubit system, so it can either be spin up or spin down, or in a quantum world it's actually both spin up and spin down at the same time.
That was Professor Michelle Simmonds, 2018 Australian of the Year, talking about how to probe the mystery of why transistors work at the quantum level, back in 2002. And that's all from us this week on Diffusion. Would you like to hear your voice on radio? Record a voice memo on your phone or use the voicemail tab on the website. We need more people contributing stories to Diffusion. Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com, and please do send me an email so I know you're listening and you'd like to hear more episodes. Please like the Diffusion Science Radio page on Facebook, if it's still around, and rate us on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Join my patrons at patreon.com/diffusionradio and support the show so I can make more episodes. The news music was Rhinos theme by Kevin MacLeod of Incompetech.com. Sound checking and fact checking by Charles Willock. I produce Diffusion, which is broadcast around Australia to 27 stations on the Community Radio Network, including 2RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, and 7LTN City Park Radio in Launceston, Tasmania. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 900 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Go to the Diffusion website to find the link to vote for Diffusion in the Australian Podcast Awards. Subscribe to the Diffusion YouTube channel on youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.